Hi everybody, today we're going to be looking at lesson 1.2 in our Springboard books. Make sure you have that out. We're going to start on page 9. Okay, so we're going to start on page 9 like we have right here. And our learning targets for today are to use patterns to write expressions. So carrying on what we saw in lesson 1.1 with observing patterns in data. And then we're going to use tables, graphs, and expressions to model situations. So once again, building on what do we do when we're given a set of data, a sequence, and how do we deal with that and make it a little bit easier for us to use. Okay, so for your warm-up for today, what you should have done before you watch this video, check your answers with mine and make sure that your answers are correct. Double check those answers right now and we'll go ahead and get started. Okay, so at the top of page 9, we're given this pattern. We're talking about Meising again and his family that go all over the world, apparently. So Meising and his family also visited Mesa Verde National Park in Colorado. As Meising investigated the artifacts on display from ancestral Pueblo people who once called the area home, Meising began to notice that the patterns to decorate pottery, baskets, and textiles were geometric, much like the pattern that we see right here. Okay, so we're not going to do number 1. We're going to skip over to number 2. So let's consider this right here. So this is figure 1, this is figure 2, and the third image is obviously figure 3. Okay, so 1, 2, 3. Okay, now we want to figure out the number of squares here. Okay, so if we count these up, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, so the first figure has 12 squares. All right, then we do the same thing with the next one. I'm not going to put numbers in here, but I'll count them up. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Okay, and then the next one, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Okay, now just like we saw in the last lesson, we're given just the first 3 numbers in a sequence, the first 3 terms in a sequence here. So if we're assuming that this pattern goes on forever, it says create a table showing the relationship between the figure number and the number of small squares in each figure. Okay, so we keep going with this. So 4, 5, 6, 7. We'll notice that, once again, like we saw in the last lesson, that the figure numbers just go up by 1. Really not that interesting. But if we look at the number of squares for the first 3 figures here, so we have 12, 16, and 20, we'll notice right away that this has a common difference. Okay, in this case, because we add the same number to get from 12 to 16 and 16 to 20, we know that our common difference is positive 4, or 4. So we keep adding 4 to figure out how much we get to the next term. Okay, so 20 plus 4, that's 24. 25, or 5, figure 5, that'll have 28. Figure 6 will have 32, because we keep adding 4, and then figure 7 will have 36. Okay, so that's how we fill in that table there. Moving on to the next question here. Moving on to number 8, which is on page 10. Describe any numerical patterns you see in the table. Okay, so we know that for number 8, we know that our number of squares in the pattern increases by 4, starting at 12. Okay, so that's how we can kind of describe our pattern here. Right, the numbers of inner colored squares, we're actually going to look at just the outer squares. Okay, so the outer squares rather than the inner. Okay, so the outer colored squares basically go like this. So that's going to be 12, 16, 20, and then we can keep going from there. So 24, 28, 32, 36, and so on. We can use those ellipses to help us indicate that that's going to be a pattern that keeps going on forever if we wanted to figure out the millionth term in that sequence. We wanted to see what that looks like or just see what kind of shapes there are. Okay, so for number 10, does the sequence of numbers of outer, once again, we're looking at outer outer colored squares have a common difference, and we kind of talked about that already. So the common difference is every time we go from one term to the next, we have to add 4. So our common difference is equal to 4. Okay. Moving on to the next part, looking at this as a graph here. Okay. So model with mathematics. Once again, we're not going to look at the inner colored squares. We're just going to look at the outer colored squares. Okay. So just as a reminder, we're going to have our figure number and the number of squares. As a reminder of what that looks like, so that's going to be 1, 2, 3, 4, 5, 6, 7, and then we started at 12, 16, 20, 24, 28, 32, and 36. Okay, so now when we go to plot these points, we want to think of them as ordered pairs. So this is my x value, this is my y value. We plot them at the same time, gives us an ordered pair. I'm going to use, let's say we use blue for this one. Okay, so 1 and 12. Oh, we got to actually scale our y-axis. That's important. So for this one, what I would do is I would scale everything by 4. So for instance, this right here, just make it 4, and then 8, and then 12, 16, 20, 24, 28, and 32 at the top here, and 36 at the top. Give ourselves enough room here to get all of our data in. So in this case, each figure, so 1 and 12 will be right there, 2 and 16, 3 and 20, 4 and 24, 5 and 28, 6 and 32, and 7 and 36. Now, just like in the last lesson when we talked about the number of minutes after an eruption of Old Faithful, how long do we have to wait? Just like we saw before, if we were to connect all these points with a line in between them, we notice that they make a straight line. All right, if we were to connect all these dots, that means that all of our the relationship between the figure number and the number of squares is going to be what we call a linear relationship. Okay, and that's because of the shape of what these points make right here. If we were to point them out to you again, notice how they fall on that somewhat straight line that I've made there. Okay, moving forward here. Okay, not going to worry about comparing the graphs. Use the pattern you've described to predict the number of intercolored squares in the 10th figure. Well, let's look at the outer figure. Once again, we're concerned only about the outer figure here. Okay, so in this case, we were to keep going with that pattern. So let's say we started at 32 and we ended up at 36. So remember, that's the 6th figure and the 7th figure. If we were to keep going here, we would say, okay, so the next one would be 40, that would be the 8th one, 44 would be the 9th one, and then 48 would be the 10th figure. Okay, so if we were to keep going with that, that's how we would do that. So how is the number of inner squares related to the figure number? We're not worried about that, so we're going to cross that one out. Same with number 12, not going to worry about that. Use the variable n to represent the figure number. Okay, write an expression that could be used to determine the number of intercolored squares in any figure. So once again, if we didn't want to draw it out or keep adding 4 to our sequence so many times, we could use a variable and an expression to help us calculate that number of squares. So just like we saw in the last one, we need the first term and we also need the common difference. Okay, first term in our sequence was 12, and then we know we're adding our common difference of 4 a certain number of times. Now to determine how many times we need to do that, remember, what's the little thing we include in parentheses here? If you remember, it should be n minus 1. Okay, so use your expression here to determine the number of intercolored squares in the 17th figure. So that means right here, this tells me that n is going to be equal to 17. So 12 plus 4 times 17 minus 1. That's going to give me 12 plus 4 times 17 minus 1 is 16. So if I would do 4 times 16, that's 64. So 12 plus 64, which is going to give me a total number of 76. Remember, we're looking at the outer squares here. Okay? Moving on here. Okay? Let's talk about something else. So Meising discovered another pattern in the artifacts. He noticed that when triangles were used, the triangles were all equilateral and often multicolored. Equilateral, if you look down right here, it says in an equilateral triangle, all three sides have the same measure. Okay, so in this case, if we're looking at the figure right here, right by number 17 at the bottom of page 11, what you want to notice is this. If they're all equilateral, that means that we can say that this is one here, this is one here, and this is one here. Let's go ahead and assume that for right now, for number 17. It says determine the perimeter of each figure in the pattern if each side of the triangle measures 1 centimeter. Oh, funny how that works out. Okay, so that means that for this one right here, we have figure 1. Let's go ahead and make a table here. That'll make life a little bit easier. So figure number will be my left side, my x value, and then perimeter will be my second, and that's going to be in centimeters. Okay. All right, so figure 1, well, that's easy. 1, 2, 3. So figure 1 has a perimeter of 3. What about for figure 2? Well, once again, we want to count up the sides on the outside. Okay, that's what perimeter is. Okay, so 1, 2, 3, 4, 5, all the way around. That gives me 5. So the perimeter for figure 2 is going to be 5. Whoops, let me draw a better 2 here. So figure 2, oh man, now I've done it. Figure 2 has a perimeter of 5. And then figure 3, once again, we want to go ahead and make sure we count up the outside here. So 1, 2, 3, 4, 5, 6, 7. So figure 3 has a perimeter of 7. Okay. Moving on to the next page, which is on page 12 here. Okay. It says that Meising found that he could determine the perimeter of any figure in the pattern by using the expression 2n plus 1. Using Meising's expression to calculate the perimeters of the next three figures of the pattern, use the table below to record your calculations, okay, which is on this page right here. Okay, so right here, let's see if Meising is correct. So once again, figure number, we know 1, 2, 3, 4, 5, 6, and 7. Okay. Now, to see if Meising is correct, we're going to use this on the expression he came up with, which is 2n plus 1. Okay, let's see if Meising is correct. So in this case, we're going to treat this as if it's n. So 2 times 1 plus 1. Does that give me what I had on the other side, that we had a perimeter of 3? Well, 2 times 1 is 2, plus 1 gives me 3. So he's good so far. What about for 2? So 2 times 2 plus 1. So 2 times 2 is 4, plus 1 is 5. Still, he's very good here. And then for 3, so 2 times 3 plus 1, let's see here, 2 times 3 is 6, 6 plus 1, that still gives me 7. So from here, we can determine that Meising's expression is correct. Okay, so in this case, we're going to go ahead and apply that to the next 4 figures without even having to draw them out and count out the perimeter ourselves. We're going to go ahead and we're going to calculate the next 4 terms in the figure using Meising's expression. Okay, so that would be 2 times 4 plus 1, 2 times 5 plus 1. There we go. 2 times 6 plus 1. And 2 times 7 plus 1. Okay? And what we should find is that it follows a pattern here. Okay, so 3, 5, 7, 2 times 4 plus 1, that should give me 9. 2 times 5 plus 1, that gives me 11. 2 times 6 plus 1 is 13. And then 2 times 7 plus 1 is 15. Okay, create a sequence to represent the perimeters and the figures in the pattern. Does the sequence have a common difference? If so, identify it. Okay, well our sequence looks like this: 3, 5, 7, 9, 11, 13, and 15. Once again, just like we've already noticed, it goes up by how much? Every time we go to a new term, it goes up by 2. So that means our common difference for this guy, for this sequence, is 2. Okay. All right, so number 20. Represent the relationship between the figures in the pattern and the perimeters as a graph. Be sure to label your axes and the scale on the y-axis. Okay, so for this one, once again, we want to use the data that we have at the top of page 12 to answer this question. Be sure to label your axes and the scale on the y-axis. So right here, our axis on the x-axis should be our figure number. And then on the y, remember, we're measuring perimeter here. And that, of course, is in centimeters. Okay? So now we want to remember, we want to use our table from on top of the page on page 12 to measure this. The last graph we had, we went up by 4. Let's go ahead and do 2's. So 2, 4, 6, 8, 10, 12, 14, 16, and then 18, like this. Okay, hopefully we can get a good idea of what this looks like. All right, so we graph this looking at our table. So 1 and 3 is our first one. I'm going to use orange here. 2 and 5, right between 6 and 4. 3 and 7, right between 6 and 8. 4 and 9. 5 and 11. 6 and 13. And then 7 and 15. And once again, just like we've seen already, if we were to connect these points somehow with the shortest distance between them, we would notice that they make a straight line. Okay, so once again, this is a linear relationship. Okay, so this is lesson 1.2 on sequences. This kind of supplements what we've seen so far. If you have questions, make sure you email me. On the next page, please make sure you are doing the check your understanding and the practice at the bottom on page 13. Okay, so you've got 2 sets of problems to get done by our next class. Please make sure you're emailing me if you have any questions, and I will see you guys next time.